Here's the distributed computing. It's a pretty short section and it's mostly in the slides, but I'll fire up a quick example and it describes how it's done. The motivation is basically to increase the speed or decrease the time that it takes to solve a bunch of problems. Like if you've got a large set of contingency analysis, or you've got multiple transient stability faults that you want to analyze, they can be broken up and sent to different machines or to different processors or different cores on the same machine, so that the total processing time for solving all of the contingencies or all of the faults, for example, is less than it would be if they were solved one at a time on a single computer, single processor. It works with certain processes in simulator that can be broken up. You can't take a power flow solution and make it go faster. I mean, that's just a serial process that has to run on one processor. Computers and memory are cheaper now than they have been in the past, and they'll continue to get cheaper, so we can solve bigger and bigger problems and do them faster. Some customers that are looking at tens of thousands, hundreds of thousands of contingencies, so that takes a lot of time if you do them one at a time. Lots of cheap computing, it's just a matter of putting it all to use. The way this works in simulator is it uses our automation server called SimAuto, and it uses Microsoft distributed Comm to access computing resources on other machines. So in order to make use of this tool, you have to license our SimAuto add-on, and you have to have a site license of simulator with SimAuto. With that minimum implementation, you can then run contingency analysis using the distributed computing. If you wanted to run other processes like transient stability, QV analysis, I think it can do right now, then you have to also have those add-ons with appropriate site licensing as well. Distributed Comm is what it uses to access the other machines. And of course, this does present security issues because the same DCOM could be used to distribute malicious software. So it's a little bit harder to implement this across multiple machines, but you can do it as long as they're secure and they're off the grid and they're not subject to external threats. But if you don't have that kind of setup, you can still use this with a machine that has multiple cores, multiple processors. There's a master process, so that the GUI that you look at is a single instance of simulator, running on one machine. And then you can have all these other processes running in the background, solving different contingencies or doing different transient faults and so forth. And then when each one of these is done, then it sends the results back to the master process so you see everything. So it distributes them using a pool of SimAuto instances and then farms those off. You can tell it for each type of problem that can be solved with the distributed computing, you tell it how big the chunk is. So 10 contingencies, for example, per process will go out. When a chunk is complete and sent back to the master process, then the master process will send out another chunk to the same processor. And it'll just keep doing that until everything is done. Yeah, there's only certain things that can be distributed in our process, and they're defined by what computer science people call cleaving points. So basically where you can break a problem off into an independent problem that doesn't depend on the results of any other problem. So contingencies are a perfect example. If you've got a list of 2 contingencies, the answer to the first one doesn't depend on the answer to the second one, and vice versa. They're each independent problems. They can be solved separately and independently. You don't have to solve them in a particular order. We just looked at ATC multi-scenarios, so each scenario is different and is solved independently. QV curves that you want to calculate on 100 different buses, they're all independent calculations. And then these are the tools that are available right now, and I think QV curves might be Okay, so to get this enabled, the first thing you have to do, you go over to Simulator right here, and I'm going to open the eastern.pwb case and look at that list of contingencies that we looked at in the earlier section. If we solve them all with the linear method, of course it goes really fast, but if we solve them all with the full power flow AC calculation method, then it takes a little bit more time, and that might be something that we want to speed up a little bit and that we can do with distributed computing. First thing I want to take a look at is go into simulator options right here, and then within there's a page for distributed computing. What we can do if we only want to use the local computer and not use a network, we can enter the computer's name, or we can just call it localhost. So that's what's entered right here. If we want to insert other computers on a network, we can do those, and we just type in their network computer name. It has to be accessible to this computer on the network, so you can do that. I'm just going to delete that. So in this example, because we don't have a network set up right here, we're just going to use the local computer, and then it'll tell you, you can click this verify computers available, and then it'll report how many cores are available. These other fields come into play when you're actually using it. Number of errors, like if it's trying to send a process out to that computer and it returns an error, how many times do you want to retry? We'll just leave that at 1. So it says I have 8 cores. If I'm just using the local machine, you probably need to use 1 core for my master process, and then if I'm doing any other work too, I may not want to load them all up. But if it's dedicated to simulator, I could put in as many processes as I want to run simultaneously, and this is a user enterable field right here. And if you want to lock all this stuff up, password protect it, you can put in a master password right here to protect everything. For individual computers, you can right-click on an individual record in here and then go to distributed computer records and then say add or change authentication info. So that stuff is all stored in there. If you're just using the local computer, you're already logged in, so you don't need to put any of that stuff in. So I can click OK here. And then there's a checkbox that you want to enable. Oh, and so this is within contingency analysis here. Let's go to contingency analysis in the case, and we'll auto insert some contingencies. Go to Tools, Contingency Analysis, and then click Auto Insert. And we'll use all these default options again, but then for the area zone filters, we want to make sure that's checked, and we'll just put in all of the area 25 contingencies only. So we'll toggle everything to no except for area 25. We'll leave that to yes. And then we'll insert the contingency record. So that'll put 111 in. And if I go to my options tab and I see I have the full power flow calculation method, if I run that without using distributed computing, let me make sure initially that I'm not using distributed computing. Let's clear, so we'll go down on the options tab within contingency analysis, and then also within the other tools like the multi-scenario ATC. In the transient stability analysis, you have this distributed computing page. So I'll go to that and then just decheck this so that I'm not using distributed computing. And we can see, if we start to run it, some of the contingencies solve faster than others, but it takes certainly a measurable amount of time to march through each one when it's doing them one at a time. So I'll just abort this calculation right here. Make sure I restore my reference, although I think it'll probably do that when you abort the calculation. So that's the standard way of doing it. What we can also do is we can run it with distributed computing. Within each tool, like contingency analysis that uses it, on this page I see I have an option that's related to contingency analysis. How many contingencies do I want to divide up per process? So I have a total. You might consider how many you have and how many processes you want to use. I have 110 or 111 contingencies. I can farm them, maybe an efficient way to send them out would be to farm them out, say 30 at a time. Because I've got 30 will get sent to each process, and I'm using a total of 4 processes here for my distributed computing. So it's basically just one iteration of each of those 4 processes solving up to 30 contingencies, and I can get them all done. So there's a little bit of overhead associated with launching a process and then with sending it the problems that it needs to work on by way of SimAuto commands, and then also retrieving the results back into the master process, which is the one I'm working on right here. And I can see also when I start this, I can open my task manager here in Windows, and I can see the programs that are running right now. Simulator release is my master process. That's the one that I'm looking at right now. I've got all these background processes running right now, and there's no simulators that are running right now. But when I start this distributed computing process, then I'll see instances for each of those 4 processes that are being done in the background. And the message log will also give me some indication of what's going on too. So I'll open the message log here, and we'll just kind of scroll to the bottom. And then if I click Start Run, it explains that it's using the distributed contingency analysis, and it's initializing these remote SimAuto processes and assigning different processes to them. And then if I go in here, I can see there's these 4 background processes that are all chugging. They've each got 30 contingencies that they're looking at, or up to 30, since one of them will just have 21 contingencies, I guess, and the other 3 will have 40. And then when they're done, they'll send the information back, and I'll see all of the results in here just the same way I would as if I ran them all locally, but they'll just they'll come back in chunks. I think, yeah, it's done right now, actually. The processes are done, and it tells me down here that it's finished. And of course, we've got a bunch of base case violations. All of my contingencies are solved. So that's kind of a summary of how that works. And again, if you've got multiple computers on a network, you can add those to the list, which can be really useful in cutting down the time if you've got tens of thousands of contingencies that you're trying to run. So this just explains, again, the configuration process. These options are only available on the simulator options. So like as far as inserting computers and verifying and the passwords and the authentication and all that, that's done in simulator options. And then within each tool, you can see these. If you click this button right here, it'll take you to that simulator options right there. Down here, you can edit some of that information that you can also edit here. More about how you can insert passwords. They're encrypted. You can't actually read the password off of the screen. It just puts the dots in there as you're typing. And then this is the example that we did, is with just a single multi-core computer. So it just explains the other fields, and then of course when it's done it tells you if it had any. We didn't have any errors when we were running that process, so that's good. But if it does, then it'll retry to send a chunk out again if it runs into an error. If it hits the maximum number, then it'll quit trying to send a chunk to that process that was returning the error. This is what we did with the contingency analysis. And like I mentioned earlier, computer security issues with using distributed automations. So if you're going to use this on multiple computers, you should have a separate, off-the-grid network that's kind of dedicated to this sort of thing. So, but it can be helpful in making use of otherwise unused resources and solving problems quickly. This is several years old, but it explains some benchmarking that was done at Bonneville Power Administration. It just looked at a base case of just using a single computer, no distributed computing, to do a bunch of contingencies. And I'm not sure how many were in the list, but enough that it took 45 minutes or so to run all the contingencies one at a time, and then using multiple CPUs. You get some diminishing returns, so each one of these increments is 8 CPUs, it looks like. Well, this is 7, but then 8 for each one of these. You get some diminishing returns because of the overhead associated with breaking the process up and then sending the data back and forth. With more CPUs to farm the stuff out to, that's more processes that have to be launched and more results that have to be communicated back. There's still some improvement with each step.
If you need further assistance, please feel free to look us up on the web, give us a call, send email to our support line, or if you prefer to work with a particular Power World engineer, please feel free to contact that person directly.